Greetings, folks. Professor Fiore here. And now I would like to talk about the accuracy of component models. What do I mean by that? Well, let's start with this resistor. This is ideal. So when somebody draws this symbol on a whiteboard and we start doing calculations, I've got so many volts, I've got so many amps, etc., etc. What we're talking about is a pure, unadulterated resistor. You can think of it as a resistor's resistor. It, in fact, embodies the concept of resistance. So I would often ask my students a little question, which is, when is a resistor not a resistor? And the answer is, when you can hold it in your hand. Huh? Well, basically, the thing that you call a resistor in lab is a physical model. Right? It's a physical device that tries to model, if you will, in real terms, in meat space, this concept of resistance. And it does it with, some increasing, decreasing level of accuracy, depending. It's not pure 100% resistance. There are other effects. A more accurate model of this, an improved model of the thing that you're holding in lab, would be something like this. There is a finite amount of capacitance associated across this resistor. How much is it? Well, it depends on the construction of the resistor. Might be a picofarad, might be 0.2 of a picofarad, all depends. So we try to make components, resistors, inductors, capacitors, diodes, operational amplifiers, transistors, whatever the heck it is. We try to make them as close to ideal as possible within certain constraints. And one of those constraints obviously is going to be cost. So you would notice, for example, that when you go and buy capacitors, there are many, many different kinds of dielectrics that you can purchase. And they all have increasing, decreasing levels of accuracy. In other words, how well do they adhere to this abstract concept of capacitance? Right? There's going to be an equivalent series resistance. There's going to be leakage resistance, temperature effects. There's all kinds of things that fold into here. And the question is ultimately, well, how much do you want to pay? We can get rid of some of those things through different kinds of construction techniques, manufacturing techniques. But, as they say, it's going to cost you. So, how far do you need to go? All right. And how does that relate to what we're doing with, let's say, an integrated circuit, right? An op-amp circuit, or maybe, a discrete circuit like, a transistor-based amplifier or something. All those things have models. When you're sitting in a simulator like this, and I don't care what simulator you're using, I happen to be using Tina TI right now, but I don't care whichever one you're using, when you grab a transistor, when you grab especially something bigger like an op-amp, the question of the accuracy of that op-amp always comes into play. And again, it's a question of trade-offs. You could make a super, super accurate model of, let's say, your op-amp, but the question then becomes, well, how complicated is it? The more complicated it is, in other words, the more components it have to make it more accurate, right? There's two components here instead of the original one resistor. The more components you add to make it more accurate, well, the bigger the computational hit. In other words, it's going to take longer to compute what the outcomes are, whether that's a voltage, a current, the transient response, the frequency response, whatever the heck it is, it's going to take the computer a little while longer to do that. So it's sort of a balancing act, all right? So to investigate that, what I want to do is take a look at a couple of different op-amp models. So here's a pretty basic circuit. Now there's actually two of them here. There's two different versions of the same exact circuit. So what we've got, I'll start over here. I've got a basic op-amp with feedback resistors set up in a series parallel configuration. In other words, a non-inverting voltage amplifier. So the gain on this is RF over RI plus 1. So this is going to be 4.7K over 4.7K plus 1, or a gain of 2, 6 decibels. This circuit is identical. They're both running on the same negative and positive 15 volt power supplies. They both have identical 10K ohm resistors for loads. They're both being driven by the same 1 volt peak, 1 kilohertz sine wave. What's different? Well, this op amp right here in TINA, this happens to use the basic sort of op amp choice you would get up here, right? So I'm just going to grab this and throw this down, where you can come in here and then decide, which op amp do I want, right? In this case, I just happen to choose the 741 right here, right? And you can see there's a whole bunch of parameters for that particular model. Now the other one, this one, was grabbed through the SPICE macros, all right? So also an op amp. I'll just open this up. There's a ton of macros in here. So if we go down here, we can go through and eventually you work your way through here. You can find, oops, I think I just passed it. You can find the MUA 741. There it is right there. Okay. Well, guess what? Those two models are not identical. Yeah, they aren't. Models are not perfect. These are trying. It's kind of funny when you think about it. It's a model of a model, because you have this ideal op amp, which, by the way, you can get a sort of an idealized op amp right here, right? Ideal op amp. And if you grab this and bring it out, you'll notice one thing about it immediately. It doesn't have power supply rails. How realistic is that? It's the most ideal op amp you can come up with. And the same thing is true if you go through the semiconductors and you grab, an ideal NPN transistor or PNP transistor. It's not going to be reflective of a real world component. But in any case, the component, let's say a 741 op amp, exists in reality, and it tries to become this ideal op amp. So it's sort of a physical model, or a physical realization might be a better way of saying it, a physical realization of this sort of idealized concept of op amp. And then what we do is abstract that one more level. We come up with a model of that physical realization of the concept. Okay, it's not a philosophy class, but bear with me. So the question is, when I compare this one to this one, is there, a practical difference in terms of my simulation results? I can say, well, there's going to be a computational difference, and maybe it's negligible if I'm just doing a single stage, 2-stage, 3-stage amplifier, but in a much larger schematic, maybe it's going to be a performance hit. I'm going to have to hang around for, a few more moments to get my results. All right. Ultimately, the question is going to come back to, is the model good enough for your needs? So very often, if you, watch some of my videos and I'm doing a frequency response or, whatever the heck it is, and I'll say, oh, well, we're within, the simulation's within 10% of what we calculated. That's good. We're happy. All right. Well, you would think, geez, it's a simulation. Why am I not within a fraction of a percent? Might be, but, I don't seem to get really upset about that. Why not? Well, I know, first of all, that the models are imperfect. And secondly, I know in the real world, the physical realizations have their own fluctuations, their own variations from part to part, plus all the other components. So if I do a simulation and I find out that, let's say, the frequency response is within 5% of predicted, I'm not going to get upset about that because, well, look, I got a couple resistors over here, and in the real world, they might be 5%ers, and if they just happen to be off in the right direction, one is high, one is low, geez, my gain might be off by 10%, just because of the tolerance of the resistors in the real world. Because when I buy a 4.7K resistor, I know it's not going to be exactly 4.7K. That's true with all my components. If I have capacitors, the power supplies, you name it. So it's really a question of, does this work sufficiently for what you're going after? And this is another reason why I always like to sort of do ballpark kind of approximations, in your head, so that you know where you're supposed to be in general terms, not not with 3-4 digit accuracy, but just in general terms. And then we can do the simulation and try to zero in on that, and then play with the schematic, start monkeying with values, do little what if experiments and so forth. Okay, so let's take these two, and I'm going to run through a bunch of things, and you can see, yeah, sometimes it makes a difference. Sometimes it doesn't make a difference. Sometimes the difference is inconsequential. All right, so I'm going to do a bunch of different things here. The first thing we're going to do is a transient analysis. So just bear in mind that VLOAD 1 and VLOAD 2, if these models were identical, we would get the same exact result on everything we're about to do. So when we do the transient, we should get identical results in the transient. And, to take it one step further, if I built this on a proto board in lab, I would get the same result, looking at my oscilloscope that I would see in the simulation. All right, first of all, let's just see what's happening with the sim here. So I'm going to come up and we'll do a transient, and we'll see what we get. All right. So, as I said, we have a gain of 2 or 6 dB. So here's my input, or 1 volt peak, and I can see, well, it looks like I only have one output. VLOAD 1 and VLOAD 2 are right on top of each other. In a couple of spots, like right here, you can see that this line is a little extra thick because one is laying right on top of the other. And, we can, in fact, just separate the curves, and you can see for yourself. All right, so here's your VN. Here's your 2 VLOADs, right? This VLOAD is scaled slightly off, probably because there's a small DC offset here, but basically it is going up to the 2 volts, okay? Let's just offset a little bit because, right, it's going from -2 to +3 rather than -1. Excuse me, rather than -2 to -2. Or -2 to +2, I'll get that right. All right, so that part so far is good. At least at 1 kilohertz for this signal, everything looks fine. All right, I don't have any difference between these two. All right. Well, what about a DC offset? Now remember, op amps have, unfortunately, in a non-ideal case, they do have a DC offset issue. Some op amps are worse than others, but the whole point of DC offset, the whole problem with it is you never really know how big it is. A manufacturer will give you a magnitude, but it's really more of a range that you're going to calculate. So in this case, this model is saying, well, we're getting about 400 microvolts, or about 0.4 of a millivolt. And over here it says we're getting about, a little shy of 2.3 millivolts. Okay, so the DC offsets that these two models are using are a little bit different. Now, and you could kind of come around here and poke around and look for different potentials and so forth, but it's all going to come out, a little bit different. Well, again, I'm not going to get too upset about that. Why? Because that's an individual thing from op amp to op amp in the real world. I don't really know. I could set up 10 of these and get 10 different results. Okay. I really only care about in the real world what my worst case is. And is that within an envelope that I can tolerate, for my application? Okay. The next obvious thing might be to go and look at the frequency response. All right, so I'm going to do a Bode plot and AC transfer. See what we get. Okay. So up here, right, so that's 6 dB, which is what I expect. But the upper end, as you can see, there's a little bit of deviation. So VLOAD number 1 with this model is coming out over here. It's just a smidge higher, like a dB maybe at most. But once we get past a certain point, it looks like several hundred kilohertz here, the other model is actually showing a little bit more output. And in fact, at some higher frequencies, it's several dB higher, maybe as much as 10. All right. Of course, you're in the stop band now, so it's not a big deal. But all right, that may or may not be an issue for you if you're really worried about what's happening out here. If you're worried about what's happening here, either model will work. Okay. Just a side note, when you get a SPICE model, right, a SPICE macro model from a manufacturer, because whatever simulator you're using might not have a library that includes a particular part you're interested in. Usually in the manufacturer's SPICE macro model, there'll be some comments. And remember, a SPICE macro model is just a human readable text file. So you can just load it into something like Notepad and just read what it says. And usually in the comments, it'll indicate what it does and does not model. So it wouldn't be odd to grab let's say an op-amp model, and it says, does not model distortion or does not model noise. Okay, so that's good. They tell you what the limitations are, all right? Anyway, getting back to where we were. So let's take a look at, something where we're going to push the op-amp. So we just looked at the frequency limit, but there's another op-amp limit that a lot of people don't think about, and that's the maximum output current. So a 741, the short circuit output current, its maximum load current, in other words, is about 25 milliamps. Well, if you're going to drive a 10K ohm load, you got to gain a 2 over here with a 1 volt input. Well, 2 volts, okay, that's no biggie. That's a fraction of a milliamp. But what if we really crank this down? In other words, what if I bring it down to like 100 ohms? Can you still develop, right, that 2 volts across, 100 ohms? Okay. Let's see what we get. All right, so I've got 100 ohms. So again, they're still identical circuits. And we'll do a transient analysis on here. Okay, that looks pretty good. All right, there's my VLOAD 1, there's my VLOAD 2. All right, he's good, he's good. All right, let's push it a little farther. So now I'm thinking, well, you want to go crazy? Let's go to 10 ohms. Well, now you're looking at like a few hundred milliamps to actually be able to do this. All right, I want to get 2 volts, right? I've got a 1 volt input, gain of 2, that's 2 volts. 2 volts divided by 10 ohms, at least 2 volts peak, right? Divided by 10 ohms, you're looking at 2/10 or 200 mils peak current. Well, there's no way 741 is going to do that. I mean, not a real one. Bonk. Oh, well, look at that. That's kind of interesting. All right, so VLOAD 1 shows that we're getting up to about 1.5 volts. And I will tell you right now that no real 741 is going to do that. VLOAD number 2, right, which is the one that's being obscured right now by this graph, is in fact clipping at a much lower level. Well, what's it clipping at? Well, like I said, maximum output current is about 25 mils. So 25 milliamps through 10 ohms would give you a peak value, a max value of about 1/4 volt. So let's grab this cursor and see what we get. Oh, look at that. We're getting just about 256 millivolts. All right, that's right on line. End result. Well, the accuracy of this model, right, the second model, this model, is much better when it comes to that load driving capacity, right? This is in fact modeling the 25 milliamp maximum of this op-amp. This model is not. But does that invalidate what we did elsewhere? No, not necessarily. When we looked at the transient response with a 10K load, hey, these things matched. It was perfectly good. And when we looked at the frequency response, okay, they were very, very close, except for the very highest frequencies. So again, it all depends on what your use is. I'm not going to say that one is better than the other, because better, the word better is a tricky word, or best. That's even worse, because it depends on what you're using it for. It's like people would say, well, what's the best op amp to buy? Well, it's what's important to you? Is cost important? Is frequency response important? What is it? Because you don't want to have to go overboard on this, right? What's the best car to buy? Oh, well, I happen to think that a vintage Ferrari 348 would be that's the best car, right? Somebody could say that. Well, it's not the best car if what you want to do is go down to the local home center and grab a whole bunch of mulch and manure for your garden. Okay, not the best car for that application. So you have to look at what you're using things for. So get out of that mindset of what's the best, or A is better than B. Well, A might be better than B in certain applications, but not in others. Okay. All right. That's I think a strong thing to remember across the board. It's not just something to deal with op amps. Whenever you're talking about doing some kind of simulation or just like I said, real world components, you always have to bear that in mind, right? What is the sort of variability you're going to get on real world components? How much accuracy do you need? Is the component model in the simulator sufficient for the kinds of simulations you're doing, right? If all I'm doing is some simple transient analysis things to check gain and so forth, yeah, either one of these is great. If I'm really going to push a small load, well, this one proves to be a better model than this one, right? So you just have to be cognizant of that. All right, experimenting is good, right? Try that with your simulator. You can do lots of experiments in simulators. I love them for that. You can do all kinds of cool what-if things and see just what happens. But always, 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 always have a little sanity check. Never just trust the simulator is going to give you an exactly correct output. There is an old adage in computer science, GIGO, which stands for garbage in, garbage out. If you have a model that's inappropriate, you have garbage into the simulator. And then, of course, it's just going to spit out garbage, right? You're going to have something that's nonsensical. So use your brain, right? If it was just as simple as throwing things in a simulator and you were done, well, we could get monkeys to do this. But that's not the case, right? Use your brain. All right, so keep using your brain, and I'll see you next time.